Our planet is getting warmer. That's a fact. Every year we see the signs. Glaciers are melting faster than ever before. Storms are becoming stronger and more unpredictable. The heat in our cities is reaching dangerous new highs. For decades, scientists have warned us about climate change. They have told us that the gases we release into the atmosphere are trapping heat from the sun. Now, we are living with the consequences. The Earth is like a house with the heating turned up too high, and we're urgently trying to find the thermostat before it's too late. We are looking for solutions, big and small, to cool our world down. We are building wind farms that stretch across the sea. We are designing electric cars that run on clean energy. We are planting forests to soak up carbon from the air. These are all vital steps, absolutely essential for our future. But what if they are not enough? What if the warming happens faster than we can adapt? This question has led some of the world's most brilliant minds to look beyond our own atmosphere. They are looking up, towards the vast, empty darkness of space, for an idea that sounds like it belongs in a science fiction film. Imagine a giant umbrella. Not an umbrella you would carry on a rainy day. This one is colossal, stretching for thousands of kilometers. It wouldn't be in our sky, but far out in space, positioned perfectly between us and the sun. Its job would be simple but profound, to block a tiny fraction of the sunlight that reaches our planet. Just a little bit of shade, cast from 1,000,000 miles away, could be enough to gently lower Earth's temperature. It could give us the breathing room we need to fix our climate problems down here on the ground. This is the incredible concept of a space sunshade, a truly audacious plan for planetary engineering. The sun is the source of all life on Earth. It is a magnificent fiery star that has warmed our planet for billions of years. Its energy drives our weather, feeds our plants, and makes our world a habitable place. Without the sun, our planet would be a frozen, lifeless rock hurtling through the cosmos. We owe everything to its steady, life-giving light and warmth. For all of human history, we have looked up at the sun with a sense of wonder and reverence. But that same life-giving energy is now at the heart of our biggest challenge. The problem isn't the sun itself, it's our atmosphere. Over the last century, we have pumped enormous amounts of greenhouse gases like carbon dioxide into the air. These gases act like a blanket, trapping more and more of the sun's heat. Think of it like a car parked in the sunlight on a hot day. The light gets in through the windows, but the heat can't easily get out. Our planet is now stuck inside that car, and the temperature is steadily rising. So, what can we do? The most obvious answer is to make the blanket thinner. We must reduce our carbon emissions and remove the excess greenhouse gases from the atmosphere. This is the #1 priority, and we cannot afford to fail. But this process is slow and incredibly difficult. It requires a global effort of unprecedented scale. While we work on that, the planet keeps getting hotter. This is where the idea of a sunshade becomes so compelling. If we can't cool the planet from the inside fast enough, perhaps we can cool it from the outside by turning down the heat just a tiny amount. So, what exactly is a space sunshade? The idea sounds simple, like something from a children's book. We need to cool the Earth, so why not put up a giant parasol? But this isn't a parasol for the beach. This is an object of truly cosmic proportions. It would be a vast, lightweight structure placed in space to cast a shadow on our planet. It wouldn't block all the light, not even close. That would be catastrophic, plunging our world into a sudden ice age. Instead, its purpose is to be a filter. It would be designed to gently dim the sunlight, reducing the total solar energy that reaches us by a tiny, carefully controlled amount. Think of it like wearing a pair of sunglasses on a bright day. The world doesn't go dark. You can still see everything perfectly clearly. The colors are still vibrant, but the harsh glare is gone and your eyes feel more comfortable. The materials used to build such a structure would have to be incredible. They would need to be extremely thin and lightweight to make launching them from Earth even remotely feasible. Imagine a film far thinner than a human hair, yet strong enough to withstand the constant bombardment of solar radiation and micrometeoroids. Scientists are exploring materials like silicon nitride or graphene, which are both unbelievably strong and light. The sunshade would need to be deployed with precision, unfurling like a gigantic, delicate flower in the vacuum of space. It is a technological challenge on a scale humanity has never attempted before. Where would you even put such a colossal object? You can't just place it anywhere in space. The location has to be perfect. If it's too close to Earth, our planet's gravity would pull it into a chaotic orbit, or worse, cause it to crash back down. Fortunately, physics has provided us with the perfect parking spot in space. It's a place known as a Lagrange point. Lagrange points are special locations in space where the gravitational forces of two large bodies, like the Sun and the Earth, are perfectly balanced. For our sunshade, the ideal location is called Lagrange Point 1, or L1. This point is situated about 1.5 million kilometers from Earth, directly in the line between us and the Sun. It's roughly 4 times farther away than the Moon. Where do such audacious ideas even come from? More often than not, they begin not in a laboratory, but in the boundless realm of human imagination. Long before engineers started drafting blueprints, science fiction writers were dreaming up ways to reshape entire worlds. Science fiction gave us the language and the imagery to even think about possibilities like this. It planted a seed in our collective consciousness, a sense that, with enough ingenuity, we could tackle even the most monumental challenges that face us. From these imaginative roots, the idea slowly began to migrate into the world of science. The first person to truly ground the sunshade concept in scientific reality was an American engineer named James Early. Back in 1989, he worked at the Lawrence Livermore National Laboratory, which is a place known for tackling huge technological problems. Early published a paper that laid out the first concrete technical proposal for a space-based sunshade. He wasn't just waving his hands, he was doing the sums. He calculated where it should go. The L1 Lagrange point, that perfect gravitational parking spot. He worked out how big it would need to be to reduce sunlight by about 2%, enough to counteract a doubling of carbon dioxide in the atmosphere. The answer was staggering. A disk around 2,000 kilometers in diameter. That's an immense scale, but it's not infinite. It was a number, a target that engineers could actually start to think about. His design was simple and elegant. He proposed a thin glass shield just a few micrometers thick, made from a single sheet. One of the most creative thinkers in this field is J. Roger Angel, an astronomer at the University of Arizona. He is renowned for designing giant telescope mirrors, so thinking about massive optics in space comes naturally to him. In the early 2000s, Angel turned his considerable intellect to the sunshade problem. Angel proposed a radically different approach, one born from his astronomical expertise. Instead of one giant shade, why not launch trillions of much smaller ones? His idea was to create a vast, diffuse cloud of tiny, independent spacecraft. Each one would be a small, lightweight disk, perhaps less than a meter across and thinner than plastic wrap. These flyers would be autonomous, using advanced optics and electronics to position themselves. Together, they would form a massive, semi-transparent cloud at the L1 point, collectively blocking the required amount of sunlight. It was a brilliant solution to the problem of scale. In the years since Early and Angel laid the groundwork, the idea of a space sunshade has experienced a quiet renaissance. It is no longer confined to the fringes of scientific thought. As the realities of climate change have become more urgent, more mainstream scientists and institutions have begun to study the concept with renewed seriousness. Today, research is exploring a whole zoo of different sunshade designs. Some scientists are looking at using a fine mesh of metallic wires. Others are exploring the idea of an asteroid sail, where a captured asteroid is mined for dust that is then carefully spread into a cloud at the L1 point. Major institutions are now involved. Groups like the Massachusetts Institute of Technology, or MIT, have research projects dedicated to exploring the feasibility of space-based climate interventions. They are investigating everything from the ideal optical properties of the shade material to the long-term stability of an object at L1. Let's take a moment to truly appreciate the scale of what we are talking about. It is, in a word, astronomical. To block just 1 or 2% of the sun's light from reaching Earth, a sunshade would need to be colossal. If we were to build a single solid disk at the L1 Lagrange point, as James Early first envisioned, it would need to be about 2,000 kilometers across. That's a distance greater than the length of Great Britain from its northern tip to its southern coast. Imagine a single engineered object so vast that it would dwarf any structure ever built on Earth. It's a scale that fundamentally challenges our very idea of construction. This is why Roger Angel's idea of a cloud of smaller flyers is so compelling. It breaks the monumental task down into a problem of mass production. Instead of one impossibly large object, you would need trillions of small ones. Each flyer might only be a meter across. But even this approach presents a scale that is hard to grasp. So if we need millions of tons of material, what on Earth, or off it, could we use? The choice of material is absolutely critical. It needs to have a very specific set of properties that honestly sound almost magical. First and foremost, it must be incredibly lightweight. The material must also be incredibly durable. The environment at the L1 point is, well, unforgiving. It's a place of perpetual, unfiltered sunlight. The material would be constantly bombarded with high-energy ultraviolet radiation, which can degrade and destroy many substances over time. Scientists and engineers are exploring some truly exotic options. One leading candidate is graphene, a revolutionary material made from a single layer of carbon atoms arranged in a honeycomb lattice. It's 200 times stronger than steel, yet so thin and light that a single square meter of it weighs less than a milligram. Let's say we solve the material problem and figure out how to get it all into space. How do we actually build the sunshade? You can't just send up a construction crew with wrenches and scaffolding. The assembly process would have to be one of the most sophisticated robotic ballets ever choreographed. For a large single-piece sunshade, we would likely need to build a dedicated space factory, a fab lab in orbit. Raw materials, maybe launched from the moon to save energy, would be delivered to this facility. Inside, autonomous robots would process these materials, manufacturing the vast, thin film sail in sections. Even the cloud of flyers presents a huge assembly problem, though it's a different kind. The flyers would be mass-produced, likely on Earth or the moon, and then packed into dense stacks for launch. Once the launch vehicle reaches the L1 point, it would release these stacks. The challenge then becomes one of deployment and self-organization. Getting all this material and machinery to its final destination 1.5 million kilometers away is perhaps the most daunting challenge of all. With today's technology, launching 20 million tons of mass from Earth is simply not feasible. The cost would be astronomical, and the environmental impact of thousands upon thousands of chemical rocket launches would be catastrophic. One of the most promising ideas is to not launch the material from Earth at all. The Moon, our nearest celestial neighbor, is rich in many of the raw materials we would need, such as silicon and aluminium, which are perfect for making glass or solar cells. Crucially, the Moon's gravity is only 1/6 that of Earth's. To get the components from the Moon to the L1 point, we wouldn't use rockets. Instead, we could use a technology called an electromagnetic launcher, or a mass driver. This is essentially a giant magnetic cannon, a long track that uses powerful magnets to accelerate a payload to incredible speeds, flinging it directly into space. So, we have a design, we have the materials, we have a plan to build it. But once the sunshade is floating at L1, a whole new set of challenges begins. The first is control. This vast, delicate structure, whether it's a single sheet or a cloud of flyers, would be constantly pushed around by the very sunlight it is designed to block. We would need a way to actively keep it in place, a cosmic steering system. This means the sunshade cannot be a passive object. It must be an active, dynamic system, capable of adjusting its own position and orientation with incredible precision. For Roger Angel's cloud of trillions of flyers, the control problem is even more complex. Each tiny flyer would need to be its own miniature spacecraft. It would need a way to steer itself, not with thrusters, but by using the sunlight itself. It's a distributed control problem on a scale that makes managing a global air traffic network look simple. Beyond the immense technical hurdles, there are deeper, more troubling questions. What would happen to our planet under a permanently dimmed sun? Even a tiny reduction in sunlight could have unforeseen consequences for Earth's complex systems. The climate is not a simple machine with a single dial. One major concern is the effect on rainfall and weather patterns. Some models suggest that regions like the Amazon rainforest or parts of Asia could see a significant reduction in rainfall. This could have devastating effects on agriculture, water supplies, and entire ecosystems that are tuned to a specific climate. Finally, there's the termination shock. A sunshade doesn't get rid of the greenhouse gases we've pumped into the atmosphere. If, for any reason, a technical failure, a war, a political decision, the sunshade were to be suddenly removed, the full force of all that accumulated warming would hit the planet at once. Perhaps the most difficult challenges are not technical or environmental, but human. A space sunshade would be a global technology. It would affect every single person on the planet. This raises a monumental question: who gets to decide? Who would control this planetary thermostat? Would it be a single nation, a consortium of the wealthiest countries, or a new international body under the United Nations? The politics of building, deploying, and managing a sunshade would be incredibly complex and fraught with peril. It would require a level of global cooperation and trust that humanity has never achieved before. What is the correct temperature for the Earth? A temperature that is ideal for Canada might be too hot for India. Every decision about the sunshade's operation would create winners and losers. How would we agree on a setting that is fair for everyone? The potential for conflict is immense. So why, with all these immense challenges and honestly frightening risks, are we still talking about this? The answer is simple, and well, deeply unsettling. It is because the primary plan, Plan A, might not be enough. Plan A is clear. We must drastically cut our greenhouse gas emissions, transition to clean energy, and protect our natural world. But we have to be honest with ourselves. We are just not moving fast enough. Meanwhile, the planet continues to warm, and we're getting dangerously close to tipping points. This is where the space sunshade enters the conversation. It is not Plan A. It is not even Plan B. It is perhaps best thought of as a planetary insurance policy. The purpose of studying sunshades isn't necessarily to build one tomorrow. It is to understand the option thoroughly, long before we might ever need it. The work we do now is a vital investment in understanding our options for protecting future generations from a climate disaster. One of the most compelling arguments for a space sunshade is that it could act as a temporary bridge. It could be, a way to manage the planet's temperature while we undertake the enormous multi-generational task of decarbonizing our entire global civilization. Imagine we deploy a sunshade in the middle of the 21st century. It begins to gently cool the planet, counteracting the warming from the greenhouse gases that are already in the atmosphere. This gives us breathing room. It halts the melting of glaciers, stops the relentless rise in sea levels, and prevents the extreme heat waves from getting worse. With the planet stabilized, we could then focus all our energy on the real solution. We could accelerate the transition to renewable energy like solar and wind power. As the greenhouse gas blanket gets thinner, we would gradually reduce the amount of shading. The sunshade would be slowly and carefully phased out. This leads us to the biggest risk of all, and it isn't a technical one. It is a human one. It is called moral hazard. This is the idea that if you have a safety net, you're more likely to take bigger risks. In the context of climate change, the fear is that the very existence of a potential geoengineering fix like a sunshade could make us less motivated to do the hard work of cutting emissions. They could argue that we should just keep burning oil, gas, and coal, because if things get too bad, we can just deploy the sunshade. This would be a catastrophic mistake. It would lock us into a future where we are permanently dependent on a vast, expensive, and risky life support system for the planet, while the root problem of greenhouse gases just gets worse and worse. The sunshade should never be seen as an alternative to cutting emissions. It can only ever be a supplement, a temporary emergency measure. It treats a symptom, excess heat, but does nothing for the underlying disease, which is too much carbon dioxide in the atmosphere. The goal of the research is not to create an easy way out, but to show that there is no easy way out. We stand at a unique moment in the history of our planet. For the first time, a single species holds the power to consciously and deliberately alter the climate of its own world. The idea of a space sunshade, born in the pages of science fiction, has now entered the realm of serious scientific inquiry. It represents a fork in the road, a choice between two very different futures. One path involves trusting entirely in our ability to transform our societies and economies quickly enough to avert the worst of climate change. The other path involves contemplating a technological intervention on a scale previously unimaginable. This is not a choice to be taken lightly. The sunshade concept is filled with both breathtaking promise and profound peril. It offers the potential for a powerful emergency brake, a way to protect ourselves if we find our planet hurtling towards a dangerous climate tipping point. Looking up at the night sky has always filled humanity with a sense of wonder. We see the stars and are reminded of the vastness of the universe and our own small place within it. But now, when we look up, we might also see a reflection of our own challenges and our own potential. The final frontier is no longer just a place for exploration and discovery. It is becoming a canvas upon which we are starting to project our hopes and fears for the future of our own planet. Ideas like the space sunshade are part of this new relationship with the cosmos, one where space is not just a place to go, but a place from which we might be able to help. This shift in perspective is incredibly powerful. For all of our history, we have been subject to the forces of nature. Now we are contemplating becoming a force of nature ourselves, capable of tuning the very energy that reaches our world. This is a profound responsibility. It requires us to think on longer timescales and with a more global perspective than ever before. The challenges of climate change are forcing us to grow up as a species, to see our planet not as a collection of separate countries, but as a single, interconnected system. A pale blue dot that is our only home in the vast cosmic dark. Whether we ever build a sunshade or not is a question for future generations to decide. But the act of thinking about it, of wrestling with its immense complexities, is valuable in itself. It sparks innovation in materials science, robotics, and artificial intelligence. It pushes us to cooperate on a global scale. Most importantly, it encourages us to dream big and to be bold in our search for solutions. We will need all of that creativity and courage to navigate the challenges of the coming century. The future of our world depends on our ability to work together to protect this precious, fragile home. So the next time you feel the warmth of the sun on your face, think about that incredible journey of light across 1.5 million kilometers. Think about the delicate balance that makes life on Earth possible. And think about the audacious idea that humanity might one day place a guardian in the path of that light, a high-tech umbrella in the sky. It is a story about technology, yes, but it is also a story about us. It is a story about the choices we must make and the future we want to create. It is a reminder that our potential, like the universe itself, is vast and full of wonder.